Hello, God bless you, and thank you for watching my videos. Please like and subscribe to my channel, and if so moved, contribute to sponsor my research and ongoing scholarship via the PayPal link and or whatever other means I may provide in the future. The original objective of part 4 here was to nail down Vandermonde's identity and show how it fits together with all of this. But I actually end up spending this and part 5 covering some prerequisite and, attempting to break down some stumbling blocks. Stumbling blocks for me, and I just imagine for a lot of folks. So without further ado, let's get into it. We left off in part 3 observing that Vandermondes convolution is a relationship of 3 variables. Not only is it a relation of these 3 variables, but it is a state of a larger relationship involving 4 integer variables where binomials play. Let's rename these variables so that n equals x, m equals y, and r equals d, the degree of our polynomial. Now let's take the xy Cartesian plane with our x equals 0 y-axis in green and our y equals 0 axis in blue, and the red point at the origin. And so let's say that every binomial on this lattice we've been looking at is the value of the point on the integer lattice of this Cartesian plane. So for each point, above each point, let's write x in blue and y in green. So these pairs of numbers that I'm writing out right here are the m plus n of the upper argument on the left-hand side of the original equation, and now x plus y. And that's all it is. So we just, for every point, above that point, we're going to write that, and then we're going to sum them, and then we get these numbers here, which are the upper arguments of the binomial coefficients values that are indicated by that lattice point. Pausing here for a moment, notice that number 2 in the upper left corner should be a number 3, and as I proceed here, I never do correct it. So I trust you can make adjustment accordingly. It's a 3. So over the dual symmetry of Pascal's triangle, it doesn't matter which side you're on, the upper argument is not going to change. As the name implies, the side of the symmetry you want to land on is a choice. You choose either x or y, and here we've got it again, x in blue and y in green underneath the points this time, but we're not going to add them, we're going to choose one. So let's choose the x first, and we get these binomial coefficients. And we have, the lower argument is 0 on the left side. But now look at this one. The argument is 0 across the bottom side. So that's the y. That's the other direction. So we got these 2, but they both evaluate to the same thing. So we're looking at one, we're looking at the other. That's something very important to keep in mind as we progress. Let's write in the xy coordinates of these integer points. And we have this emerging fundamental idea that we can construct a full-fledged, consistent mathematical system on just the binomial coefficients that use the binomial coefficients as from our perspective, current perspective, a proxy to a coordinate in space, but with the symmetries already baked in some way. Now we're going to do a lot of using a grid with the numbers inside because it's clearer and easier to see and whatnot. So just important to keep in mind and remember that the intersection points of the grid are not the integer points of the Cartesian, of the underlying Cartesian or the overlying Cartesian plane, and that lower corner of the lattice is the point -1/2, -1/2. Another thing that it will be beneficial to leave yourself open to the idea of is that there are going to be certain values that are in different places because of the symmetry, but are they really? What if it's the same thing but only seen from a different point of observation? I mean, so we've already looked and seen how this sort of something like that going on with polynomials, and here with binomial coefficients themselves. If we look up, we're going to choose the y, and if we look to the right, we're going to choose the x for the lower argument of our binomial coefficient, and it's the same value. In this sort of thinking of it in the other way, that it's not the symmetry. There's not two copies of something there. There's one copy, and there's two different observation points. Or I should say, you're not choosing a different point or a different value. You're choosing to look at the same point or the same value differently, or from a different direction, or from a different vantage point, like that. And ultimately, these different perspectives are not just isomorphic to each other. They're aspects of the same thing, and they are not separate things themselves. So by understanding how they work together, which is, it's all relative, laws of conservation and symmetries. So it's not like one is equal to the other. It's a way to navigate around the larger thing. But in all cases, it is just a single view that is required in order to unlock the whole. So maybe there's an aspect or a facet that you can't see from the direction you're looking or from the observation point you're at, but you can see it mathematically because you can solve for it. I imagine a perfect analogy is the way that particle physicists can predict the existence of new particles. Unfortunately, I think we make things harder than they have to be sometimes, particularly with our notational choices or conventions, and for the sake of brevity and beauty of expression of the written form of the equation, sometimes things are sacrificed in terms of understanding and making connections and being able to visualize and binomial coefficients are a great example. The standard definition of a binomial coefficient is just this ratio of the of factorials, x over k x factorial over k factorial times x minus k factorial. The pretty, simplified, elegant notation comes at the expense of taking away one of the pieces of information on the right-hand side. And depending on which of the two pieces of information on the lower argument of the expression you choose, you have a different binomial coefficient. But you don't have two things. You have two notations for the same thing. Can you hear it in my voice? That primal urge to go all Gordon Ramsay on whoever thought this was a good idea. Who cooked this up? It's almost like we put multinomials on hold, and we'll worry about those after we conquer binomials, and then we scaled the face of modern combinatorics. And of course, multinomials are there, and I'm not dismissing them in any sense of the word. I'm talking about generally, and but anyway, if we start with just multinomials in general, of course, then the next place we go is a trinomial. And that's just x factorial over a factorial b factorial c factorial, three numbers factorial taken, with the condition that the numbers underneath add up to the number on the top. Or I should say that the simplicity of that definition that ties all of the multinomials together and gives you a way to look at them as a whole is kind of simpler and easier to follow, and I think more insightful than looking at binomials alone and then trying to go to something else when they were the same all along. And obviously it's not as simple as that, but it's a good time to stop this video, and I'll pick up on this in the next video, and let's explore multinomials there. See you then. In the meantime, please like my videos, subscribe to my channel, click that bell notification icon if you'd like, but please click that PayPal link and donate to support my further scholarship and research. I have parts 5 and 6 already uploaded, and for anyone who donates prior to publishing those, I will send you a private link so that you can watch them in advance. So if you do donate, please make sure to include a valid email address in the comments on the PayPal donation form so that I know where to send the link to you. And if you want to collaborate with me and improve these videos and see what it's all about in advance and get involved, then please donate and contact me. Thank you, and God bless you.